part B of this problem, what we're looking for is a line that is perpendicular through point C. So if I just take this AB and I extend this AB out, and I find a perpendicular line through C, okay, and it's going to intersect the x-axis at another point we'll call D2. So this point here is going to be our D2, and it's going to have a coordinate of A and 0. And what we need then is to find the slope in this case of the perpendicular line. So first of all, the slope of AB is equal to 4 over 3. So slope of the perpendicular line is going to be negative 3 over 4. And using that, I'm going to do this. So I've got my slope triangle here. I still have the change of y as negative 8. Okay, so my change in y over my change in x is going to be negative 3 over 4. And my change in y, for my diagram here, I'm going to go 8 down. So I'm going to go minus 8. And I want to find out my change in x here. So my change in y is negative 8. And then I need to find the change in x. And I can find the change in x algebraically. So I end up with change in x is equal to negative 32 over negative 3. And that's going to be my change in x. So if I want to find the position of A, we'll call A2. So A2 is going to be, well, I start at 9, and I'm going to have a change in x of 32 over 3. And so that works out to be 27 over 3 plus 32 over 3. So my position A2 works out to be 59 over 3, or about just under 20. Okay, so that's approximately 20, a location of 20, 0, and that's going to give me this line through point C, which is perpendicular to the original line AB. So it's going to be 90 degrees there, and it'll pass through that point which we called A2. For this last problem here, we have two parallel lines, and we want to find the shortest distance between the two lines. Now the implication is that the shortest distance always is at 90 degrees. Okay, so that line is going to be 90 degrees. And we do have some measurements here. So I'm just going to redraw that down here, maybe 90 degrees here. And we do have some distances because we have coordinates. And we can see that the y-intercept is at 6 and the y-intercept here is at negative 3. So we have this distance here. Distance between the lines is 9. Now the problem is that distance is a vertical distance. We could also find a horizontal distance, but notice that that red line is neither horizontal or vertical. So I'm just going to find my horizontal distance here. I'll do it in blue. So maybe I'll just choose that y-intercept point. If I just go across, I can see that that's exactly 3 units across. Okay, so if I take a look at the differences in my zeros, this is going to cross 0 at negative 2. This is going to cross 0 at positive 1. Yeah, that's a horizontal distance of 3 apart. And that vertical and horizontal distance stay the same relatively through that whole line. So anywhere on that line, I can draw those two vertical and horizontal lines between the two lines. Now, again, the problem is that the line that I'm looking for is neither horizontal or vertical. It's this kind of diagonal line here, and I cannot use either of those lines to calculate it. But when I draw that perpendicular line, because I already have 90 degrees here, that perpendicular line splits it into two triangles which are the same shape and has the same rise and run as this bigger triangle here. And so what I'm going to do is I'm going to find the length of the hypotenuse. So 9 squared plus 3 squared gives me root 90 across. That's the length of the hypotenuse of this big triangle. So I've got my big triangle here that's not a very nice line. Anyways, I'm gonna leave it like that. So that line there is gonna be the diagonal of my big triangle. And the triangles that I formed are gonna be similar in shape to that big triangle that I have out here. So this line here, I'm just gonna draw a little bit better. At 90 degrees, these two smaller triangles are exact same shape. With the exact same shape, they share the same ratio of sides. And I can then use the big triangle and compare it to the smaller triangles. So here I've got this side D is relative to this blue side 3, and I can write it as a ratio. So the smaller triangle D compared to the bigger triangle, the same side to the bigger triangle. So I have small to big comparison. I can make the same small to big comparison on some other side. So I'm going to use a hypotenuse here of 9 and use the hypotenuse of root 90. So small hypotenuse compared to the big hypotenuse, small to big comparison. And then I can solve for side D. D works out to be 27 over root 90. Simplifying that, that becomes 27 over 3 root 10, or 9 over root 10. So there is the shortest distance between the 2 points. Sorry, between the 2 lines. Okay. Now I figure I show you a formula that you can use to find the shortest distance between a point. So this is the formula for distance between point and line. The formula looks like this. The distance is equal to, and this is going to be in general form, so a x naught plus b y naught plus c, if this is a general form coefficients a, b, c, over a squared plus b squared. So the coefficients on a and b is the x and y is going to show up in the denominator here. And so what I can do then is take one of these lines, put it into general form, and then find a point on the other line and use that point to calculate this distance. So I'm going to take this line here and just rewrite it in general form. So 3x minus y minus 3 equals 0. And then I'm going to take a point on the other line. So this line here is going to be, and I'm just going to use the 0 here. Okay, so I'm going to use the coordinate -2 and 0. And by doing that, I can find the shortest distance between that point and that line, and that will represent that distance, same distance that I calculated here. So I should end up with this exact same value of 9 over root 10. So let's try this formula out. So the distance is equal to, okay, the absolute value of a, so that's 3, times the x coordinate. Okay, that's going to be -2. So 3 times -2 plus 3 times -2 plus b is going to be -1. So I'm going to go minus b, and then I'm going to plug in my y coordinate into that position. Okay, so 0 plus c, so that's going to be -3. So notice how all I've done is taken this general form equation, that same one there, taken the coefficients, and plugged in my x and y of the point that I want to find the closest distance to. And then I'm going to divide that by a squared plus b squared. Okay, and then calculating this out, I'm going to end up with the shortest distance between those 2 points is going to be -6 minus 3 absolute value over 9 plus 1 is 10. So I end up with absolute value of -9 over root 10, and I get the exact same value there. So this formula is actually quite handy if I want to find the distance between a point and a line, the shortest distance between a point and a line. I could also use this similar triangle argument to find this distance if I can relate the similar sides to each other.